All right, welcome. In this video, we're going to be starting a new unit, a unit about radicals. So things like square root and cube root. And in this video in particular, I'm going to be going through, the 8-1 notes, but I'm going to be focused on just the numbers, like simplifying radicals that just have numbers on the inside. And then in a separate video, I'll record myself going through the algebraic expressions. So it'll be really important for us to start with the definition for, just to remind ourselves what this means. The nth root of a number can be written as the nth root of a where n is called the index. Okay. For example, the fourth root of 16 can be written as, fourth root of 16 and is equal to 2 because 2 to the 4 equals 16. And if there's more than one number that you could take to a given power and, get the thing back, the radical sign is going to indicate only the positive root. Okay, so basically by square root, we mean the positive square root. And then we need to be reminded about these properties that we've hopefully learned about in an earlier class. Now maybe that third one at the bottom, that looks a little unfamiliar to you. That could be the case. That's, I think, typically like Algebra 2 is when you start thinking about these fraction exponents, but I'll show you all about that really when we go no, we'll talk about that in this video. Okay, but let's talk about some examples. If we're taking the root of a product, that's the same as the product of the roots. So the square root of 36, I can write, on one hand, I know that's 6, right? That's kind of the point here. So on one hand, I know this is 6. But on the other hand, I could say that this is the square root of 9 times 4, right? Because 9 times 4 is 36. And then that would be, using the property, the square root of 9 times the square root of 4, which is 3 times 2. So, it was a very long way of showing that the square root of 36 was 6, but it fits with this property. So that's good evidence that this is true. Okay. This is not true over addition. The nth root of x plus y is not equal to the nth root of x plus the nth root of y. Okay. And then the square root of 100 over 25, okay, we know that's the square root of 4, right? Because 100 divided by 25 is 4, so it's going to be the square root of 4, and it's going to come back 2. But it might be good for us to look at, how the property works. So the root of a quotient is the quotient of the roots. So divided by the square root of 25. And that's going to equal 10 divided by 5, which is the 2 we were expecting to get. Now, the fact that the nth root of x is x to the 1 over n power. Even now, having delivered this lesson a couple of times, I'm not totally sure how much detail I want to share in this video. But I think, in the interest of keeping this video as short as possible, but also giving you the details you need to understand what's going on, I'm going to start with the 1/2 power. Okay? And so what we're saying here is that the square root of x is going to be x to the 1 divided by 2, because if there's no index, it's implied that it's 2. Okay, let's think about what would happen if we multiplied x to the 1/2 by x to the 1/2. We would add the exponents, right? So that would be 1/2 plus 1/2 is 1. But the type of number that if you multiply it by itself and you get, I didn't quite say that right, but we also know that the square root of x times the square root of x is equal to x. And so that's kind of like the evidence that I'm saying at this point. We'll see more evidence of this, as we move forward. All right, now let's kind of lay down the rules for what is going to be fully simplified when it comes to radicals. So there's going to be a lot of problems. There's hey, give your answer in simplified radical form. And, with kind of the implied threat that if you don't give the answer in simplified radical form, you won't be fully correct. So let's be really clear about what we mean by simplified radical form. Okay, the first thing is going to be no unreduced radicals. Okay, so two examples of unreduced radicals would be the square root of 16 and the square root of 24. The square root of 16, this is unreduced. Oh, we know it's 4. Okay, but the square root of 24, that's something we're going to have to do a little bit more with. Now, I'm going to have a bunch of examples in this video, but my recommendation for you is to think of numbers that divide 24 and think if any of them are perfect squares. And maybe you've got a list, on a sheet of paper somewhere. 1, 4, 9, 16, 25, 36, 49, and so on, right? All your square numbers. And think about, are any of these dividing this number? Okay, well, 1, 4, 9, 16, 25. Okay, 16 doesn't divide 24, but 4 does. Okay, so I start with, 24, that's 4 times 6. So I'm going to write it as 4 times 6. I'm starting to run out of room here. So I'm going to say that that's equal to the square root of 4 times the square root of 6, using that radical property. I'm just going to have to keep scooting this over. And then the square root of 4 is 2, so I'd have 2 square root of 6. Okay. And that would be fully simplified, because the square root of 6, there's nothing I can do with that, because 6 isn't a perfect square. Okay, and it doesn't have any factors that are perfect squares. Its factors are 2 and 3, and those aren't on our list. Okay, so that would be us, dealing with any unreduced radicals. The other thing that we have to be careful about is radicals in the denominator. Okay, now I'm going to show you how this could happen and what we do to fix it. But I think the discussion on radicals in the denominator, why do we even care? I'm actually going to save that for a different discussion. So the example I want to bring up that would cause a radical in the denominator is find the value of x, right? Here we've got a 45, 45, 90 triangle. The hypotenuse is 1. What's the value of x? So we're going to just write down what we know to be true, which is the Pythagorean theorem. For a right triangle, a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. In this case, that would give us x squared plus x squared equals 1 squared. So that's 2x squared equaling 1. If I tried to solve for x, I'd end up taking, all right, x is plus or minus the square root of 1/2. Now, we're looking at the lengths of a triangle, and this is algebra 2, right? Maybe I've told you that in pre-cal we'll look at triangles where some of the legs are negative. This isn't pre-cal, right? We're only going to be interested in where this triangle has positive leg lengths. So let's just think about the positive square root of 1/2. Okay, so the square root of 1/2 is not in simplified radical form because I've got a square root of a denominator. Okay, so what I would say is that, the square root of 1/2 is equal to the square root of 1 over the square root of 2. And we know the square root of 1, but we don't know the square root of 2. So we would say 1 over the square root of 2. And while in some classes it's acceptable to leave this as the answer, in Algebra 2 this is not going to be a safe place to stop. Okay? We need to be able to rationalize the denominator, specifically because standardized tests that are multiple choice in our area like SAT, ACT, the answer choices are always going to be in simplified radical form. They're not going to have square roots in the denominator. So if this was the answer to a question on your SAT or PSAT or ACT or some kind of standardized test, you wouldn't see this number. You would see this number after a little bit of work done to it. So what I'm going to do is I'm going to take this number and I'm going to multiply it by 1 so I'm not changing the value. And I'm going to multiply by root 2 over root 2. And you've probably seen this before, like in a geometry class. But 1 times square root of 2, that's root 2. And then in the denominator, root 2 times root 2, well, that's going to be 2. And so that's going to be, x in simplified radical form is root 2 over 2. Okay. Now, if you are interested in why a person would care about this, why do they on the standardized tests only write it with no radicals in the denominator? Well, then I'm going to just encourage you to watch this video. I think you could probably click a link right about here, and that would redirect you to a different video on simplified radical form or rationalized denominator, why do we care, something like that. But I'm saving that for a different discussion because I'm just showing you how to work with these things right now. All right, so let's simplify some expressions, right, with numbers in them. So the square root of 16, that's 4. The square root of negative 16, that's still in play, right? We just learned about that in the last unit, so that's the square root of 16 times the square root of negative 1. Square root of negative 1 is I, so this is 4i. Okay, the cube root of negative 125, that's okay. Okay, we're going to split it up, the cube root of 125 and the cube root of negative 1, just like we did with the square root. But the thing is, the cube root of negative 1, that's not I. That's negative 1, because if I take negative 1 to the 3rd power, I will get negative 1. So I've got cube root of 125, I'll just tell you that's 5, and cube root of negative 1's negative 1, so that's negative 5. And then cube root of 125, I just told you that was 5, so there you go. All right. Now, I think unfortunately, I already did square root of 24 in this video, so, well, not much to be done there. Just like before, that's square root of 4 times square root of 6, that's 2 root 6. Thinking of square numbers that divide 24. This one, okay, I don't think I told you about simplifying a cube root. It was the same idea. Thinking about a cube number that divides 32. And our cube numbers are 1, 8, 27, 64, 125. Okay, past that, 216. It takes me a while to think of them. Okay, so we're going to mainly stick with lower cube numbers. But 8 is a cube number, and that divides 32. So I'm going to say this is the cube root of 8 times 4. Just use that radical property. Cube root of 8, cube root of 4. That's 2 cube root of 4. That's how we simplify. Okay, cube root of 81. 81 is 9 times 9. I'm looking for like 3 things. But maybe I could write cube root of 81. This is another way. I wouldn't typically do this, but I kind of had the thought. It's 9 times 9, and 9 is 3 times 3. So I've got in total 4 powers of 3. Okay. And, well, the 3 of them here, if I've got the cube root of 27, or the cube root of 3 times 3 times 3, this is going to be 3, right? So that's going to be 3, and then I'm left with the cube root of that extra 3 there. So 3 times the cube root of 3. Okay, and then the last one, square root of 27. I'm thinking what divides 27 that's a perfect square? 9. Okay, so square root of 9, square root of 3. Square root of 9 is 3, so I'd have 3 root 3. And now, because powers of numbers and variables is going to be like a huge theme, really, for the rest of the year in Algebra 2, I need to remind you about the exponent properties we've already learned about. So this thing here where we're multiplying 7 to the 3 times 7 to the 2, that's where we're going to add the exponents. 7, and just to remind you why that was the case, 7 to the 3 times 7 to the 2, and that's going to be 5 total 7s multiplied together. So that's 7 to the 5. We add the exponents. And with 11 to the 8 over 11 to the 6, I'm not going to write out 8 copies of 11, but we could do this canceling off on top and bottom, right? Because 11 divided by 11 is 1. And so 6 of the 8 will cancel off, and I'll be left with 2 in the numerator. So that's equal to 11 to the 8 minus 6, which is 11 to the 2. And I know that. That's 121. 7 to the 5, I'm not sure about that. And I don't have a calculator nearby, so I'm not going to be doing that. Okay, and then 3 to the 2 to the third, power of a power, we're going to multiply those exponents, right? Because it's 3 squared times 3 squared times 3 squared, and then we would just kind of add those exponents. Is another way you can think about it. But I was reminding you of those exponent properties. All right, now let's do some work on rationalizing the denominator. So this is where we need to make sure that the denominator of our fraction is not a square root, right? It's just a it has no square roots in it at all. It's just a regular integer. Okay. With this, we're going to probably start off with saying that, hey, that's square root of 5 over square root of 3. And then we're going to multiply by a clever form of 1, just the right form of 1 to get this root 3 out of the denominator. So I'm going to multiply by root 3, so this can become 3. But to be fair, I need top and bottom by root 3, so I'm multiplying by 1, so I'm not changing the value of this fraction, right? So when I multiply root 5 times root 3, this is kind of going to be applying that radical property in reverse. That's going to be root 15. Divided by root 3 times root 3 is 3. That's us rationalizing the denominator. Okay, the next one's a little trickier. Okay, that's going to be 2 divided by 1 minus the square root of 3. Now, I don't know if you already know how to do this or not. Okay, but what we're going to do with this is we're going to multiply this by another clever form of 1. But I think you would find if you multiplied on top and bottom by square root of 3, you wouldn't get all of the radicals gone. So what we need to do is multiply by the radical conjugate. And we've never actually done this, but we've multiplied things like this together when, dealing with polynomials with irrational roots. And so this operation should feel a little bit familiar. So I'm going to say, okay, the radical conjugate of 1 minus square root 3 is going to be 1 plus square root 3. And I got to multiply by 1 to be fair. And so I'm going to go ahead and actually multiply that out and say this is going to be 2 plus 2 root 3 divided by, okay, over here I'm going to do, distribution. I'm going to FOIL. 1 times 1 plus root 3 minus root 3 minus 3. So this is equal to 2 plus 2 root 3 divided by, well, these are going to cancel off, and that's why we chose the conjugates. That always happens when you do that. 1 minus 3 is negative 2. Now, on the recent test this year, I saw, we were grading some, and I saw, situations with the quadratic formula where it looked like that, and people were just dividing the 1 and not the second coefficient. Okay, remember that if we're dividing this whole thing by -2, then we're going to have to divide both of them by -2. So this is going to be equal to -1, 2 over -2. 2 over -2 is another -1, so minus the square root of 3. That's how we're going to rationalize a denominator situation like that. There's another situation you need to be aware of when rationalizing denominators. That would be cube roots in the denominator. So 1 over the cube root of 10. So I always, telling people about this, I always ask, like, hey, what do you think you should do? And typically people think they should multiply by cube root of 10 over cube root of 10. But then you might realize that's not going to work, right? Because the only reason that this was effective is that the square root of 3 times the square root of 3 is 3. But the cube root of 10 times the cube root of 10 is not 10. It's the cube root of 100, which is, I don't know, less than 10. And so what we're going to need to do is we're going to need to do this again. Just repeat the process. So I'm going to multiply by cube root of 10 over cube root of 10. And then over here, I'll have 3 cube roots of 10. If I multiply that all together, I'm going to get 10. That's what it means to be a cube root. It's the number, if you cube it, you get 10. Okay, but then, and I don't know exactly what the best way is to write this, but I think you could write cube root of 100. You could also write cube 10 squared. And that's going to take us to the next thing we're talking about, which is where the exponent is a fraction. All right, now let's think about this a little harder. What's going to happen with cube root of 10 times cube root of 10? That was the numerator of the fraction in the previous example. Okay, if I just take a step back and I say, hey, I'm taking a number and multiplying it by itself, that's like squaring it, right? So I can say that's cube root of 10 squared. And now, one of the radical properties that I really haven't used much yet in this video, but I will be using extensively, is that the cube root is the 1/3 power. So that's 10 to the 1/3 squared. And we know about our exponent properties. This is where we multiply exponents, right? So this ends up being equal to 10 to the 2/3. This cube root of 10 squared. And so we'll be, let's look at this a little more formally here. All right, so we've talked about rational numbers in this class, and so rational exponents are just going to be exponents that are rational numbers. A rational number is what you might think of as a fraction. Okay, so we're over here, and a rational exponent is an exponent that can be expressed as m divided by n, where m and n are integers and n is not 0. Okay. We can write any radical expression as an exponential expression, just having a fraction exponent. Okay. The denominator of the rational exponent becomes the index of the radical. That's really important. All right, so if an exponent is of the form 1 over n, so you've got like some number taken to the 1 over n power, we're just going to write that as the nth root of x. Okay, and hopefully if it's a number, we'll be able to figure it out, or at least simplify it and put it in simplified radical form. Okay, but if an exponent is of the form m over n, I'm going to recommend that you look at this as the nth root. Deal with the denominator first. Nth root of x taken to the m power. And my advice to you is always going to be to deal with the denominator first. And you'll see why. I'll show you just like in the next example why you need to take the root before taking the power. Okay, so we're going to want to do it. That said, this is the same as x to the m's nth root. But this is going to be harder to compute. So let me just show you what I'm saying. All right, so immediately, this first one, this is going to be the perfect example. So negative 125 to the 2/3. What I'm saying is deal with the denominator first. 2/3, that's the third root. So I'm going to take the cube root of negative 125, and then I'm going to square it. Because otherwise, my other option was taking negative 125 and squaring it. I don't know what 125 times 125 is. Maybe you're some number sense expert and you do, but that's not me. So I gotta know myself and say, okay, I can take the cube root of negative 125, but I don't. And you might be a number sense expert and you might know how to take 125 to the second power, but I suspect you might not know the cube root of that number. Food for thought. So over here, I'm going to take the cube root of negative 125. That's going to be negative 5. I'm going to square it, because that's what I've been instructed to do, right? Still taking that to the second power, and that's going to be 25. Okay. 64 to the negative 1/3. Remember that the negative power just turns it into a fraction, so it's going to be 1 over 64 to the positive 1/3. Okay, the 1/3 power, that's going to be the cube root. Oh, barely enough room, but I can't fit that. 1 over the cube root of 64. Cube root of 64 is 4, so this is going to be equal to 1/4. Right, 4 to the 5 halves, it's like 4 to the 2.5. Okay, we're going to take the square root of 4 first, and then take that to the 5th power. Okay, so that's 2 to the 5, and that's going to be 32. 81 to the negative 3/4. Okay, well, I'll take the 4th root of 81 to the negative 3. Okay, we could have said this is 1 over 81 to the positive 3/4. Decided I'd take a different approach this time. Okay, the 4th root of 81, and if you're having trouble thinking of a 4th root, you're not too many I'm going to ask you to take, but you can take a 4th root by taking a square root and then taking the square root of that. So if you take the square root of 81, that's 9, the square root of 9 is 3. So I've got 3 to the negative 3, and that's going to deal with the negative exponent, 1 over 3 to the positive 3. 3 to the 3 is 27, so that's 1 divided by 27. Okay. And then 9 to the 3 halves, okay, we're going to deal with the half power first. A half power is a square root, so it's the square root of 9 taken to the 3rd, that's 3 to the 3rd, and that's 27. All right, now here's an example that I promise you is going to be on your quiz next time if you're in my class. Write the expression using a rational exponent. Okay, so this is supposed to be like the easy question for you. Okay, make sure you learned a little bit of something last time, today, whenever you're watching this, or learning this. What we're going to do, the base of the exponent is still the base of the exponent. Just remember the index of the radical is the denominator of the fraction, so we're going to divide by 4. 3 divided by 4. 11 to the 6 over 3. Okay, I'm just going to stop there. I mean, I know that's 11 to the 2, and I also know that's 121, but stop there. I think we also just did this one. Okay, so I'm just going to call that 81 to the 3/4. Remember, the index of the radical becomes the denominator of the fraction. And then the cube root of 10, I'm going to call that 10 to the 1/3 power. Okay, make sure we're definitely able to do that. All right, now let's just wrap up with a couple of more examples. These are kind of random. I'm not sure what exactly they're getting at. I haven't really thought about them. I don't know that I worked these in class when I was delivering the lesson in person, but I see some good stuff here. And it's never a bad time to practice our exponent properties, right? So if we're multiplying two things and they have the same base and different exponents, we're going to add the exponents. So this is going to equal 25 to the 2/5 plus 3/5. If I have 2/5 and 3/5, that's going to add up to 5/5. And 5/5 is 1. And 25 to the first, well, that's just going to be 25. Okay, here when we're dividing two things that have the same base and different exponents, we're going to subtract the exponents. So I'm going to have this equaling 8 to the 1/3 minus 2/3. That would be 8 to the negative 1/3. Okay. The 1/3 power is the cube root. The negative 1/3 power, so it's just going to be 1 over 8 to the 1/3. Got room for that. And so that's 1 over the cube root of 8, and that's a half, right? Because the cube root of 8 is 2. So those were a couple of simplifications that we definitely need to be able to do with numbers. All right, we got two more for you here. I think this one's going to go pretty much the same as number 1. We're going to same base, different exponents. Add the exponents. 3/8 plus 1/8 is 4/8. Okay. Now I might say that that's 4/8 is the same as a half, and I know that the half power is the square root, so I'm just going to write that as square root 3. But I don't know that this is any more simplified than that. I think these are an equal amount of simplified. All right. And then, if it doesn't say like radical form. Radical form, okay, that's radical form. Okay, negative 8 to the negative 1/3. Maybe I'll say, okay, the negative power is going to make it 1 over negative 8 to the positive 1/3 power. And remember, the positive 1/3 power is the cube root. So that's 1 over the cube root of negative 8. And the cube root of negative 8 is going to be negative 2, because negative 2 to the third is 8. And so that's going to be 1 over negative 2, and that's going to be far enough. All right, now lastly, maybe you're feeling like you need more practice on this. If you are and you have my notes book, you can go to page, 8, and do this simplified radical form extra practice. I am not going to record myself working all of these. That would make this video really long. I'm just going to flash up the answers right now. Okay, so if you were wanting to check your work, you should probably pause and work them, and then check your answers here in a couple of seconds. All right, here you go. That was a lot. Oh no, I forgot to go back in and do 76, but I think 76 is going to be divisible by 4. If I divide, so I'll just show you how I was mentally doing these. Okay, if I'm dividing 76 in half, that's going to be 38, and half of 38 is 19. So I've got 19 times 4 is, I believe, 76. Yeah, and it's just shy of 80. That makes sense. So the square root of 4 is 2, and the square root of 19 is not something I'm going to be able to work with, so I just put that there. Okay, so here you go. Here are all of these. Okay, if I'm wrong about any of them, or you don't understand how I got any of them, I would encourage you to come see me in the morning, contact me, or leave a comment or something. But that's going to be all for this video. So thanks for watching.